Okay, let's solve the fourth problem. Find the conjugate antisymmetric part of x of n. So the formula for that is 1/2 times the sum of our original waveform minus x conjugate of negative n. So for this particular example, it's probably easiest, because this is such a finite length sequence, just to enumerate all the values. So our x of n looks like 2, 3, 1, where that's our center component, -3, -2. And from that, we're going to subtract the same thing, but flipped, negative n. So that'll be -2, -3, 1, 3, 2. So we've just reversed the order of that waveform. 0 points the same. And we still need to take the complex conjugate. Since this is real, the complex conjugate's the same as the waveform, so we don't need to change that. We can just take off it's its own complex conjugate, so we can just take off the complex conjugate symbol. And now we can subtract. So that will give us 2 minus -2 is 4, 3 minus a -3 is 6, 1 minus 1 is 0. Say -3 minus 3 is -6, and this will be -4. And to this we'll multiply 1/2. And our center index remains in the middle. This particular waveform is non-zero for -2 to +2. If instead it had extra values out here, say, you might have to zero pad to the left so that you could add them up and have items align. But this is the conjugate antisymmetric part, and a quick check. If we were to graph it, it didn't ask us to, but if we were to graph it, what did I do wrong here? It should have been 2. It's useful to graph it. It can help catch errors. So now that I've graphed it, quick check to see if it is conjugate antisymmetric. If I flip the axis horizontally and then vertically, I'll get the same waveform. And so therefore I know that it is indeed conjugate antisymmetric.